Are you ready?
Yes.
Okay, so let's start your talk.
First, thank you for introducing me, Mr. Chairman. Hello everyone. I'm Jae-Hun Cha from Gcce National University in Korea. Today, I will present Markov model-based reliability analysis of LED driver system with on-load redundancy. This is index before the presentation. I will explain the motivation and background in introduction. And I will explain in the following order: characteristic LED driver and reliability analysis and conclusion. This page is introduction. The motivation for writing this paper is increasing use of LED drivers in various applications. We can absorb this easily in real life, such as a paper commercial billboard has been changed to LED display for advertising. Not only this one, but also school blackboard is changing to LED display blackboard in school. However, LED driver accounted for about 59% of all failure in lighting system. It means that we have to prepare for potential breakdown. And the importance of redundancy in industry is also growing. Despite their importance growing, there's still lack of research about redundancy. Therefore, we analyze evaluation of reliability increase according to redundancy. The following page is background. As we know, the LED application is growing very fast. Especially, traffic electronic sign is related to safety, and commercial billboard is related to money. So, if failure occurs in these systems, it can cause big problem in safety and business. To prevent these problems, there are two types of redundancy. The first one is cold standby. The cold standby is backup module only work after failure. The figure below the table, one module failure occurred, another module replaced it and keep working. So the cold standby has downtime while recovering. In contrast, the on-load redundancy is module share the load in real time. So when one module failure, another module keep working immediately and share the load. So it doesn't have downtime while recovering. This is why on-load redundancy system is important to traffic sign and billboard, where continuous operation is important. This page is characteristic of LED driver. The structure on the left is LED driver with on-load redundancy. We analyze the redundancy of LED driver with a boost converter structure. The operating principle is simple. First, receive rectified the AC input voltage, boost it, and output it to the LED stream. We assume this structure uses on-load redundancy and through the on-load structure with parallel output, the output remains constant even if a failure occurs. And the figure on the right shows the billboard structure what we analyzed. And it consisting of a 12 LED driver 4x3. This page shows LED driver components and failure rates. The table on the left shows main components of the LED driver. There are MOSFET, potentiometer, inductor, resistor, aluminum capacitor, and so on. We calculate this component failure rate using FIDES 2022 guide. And the graph on the right shows the failure rate according to temperature. Here, the x-axis is temperature, and the y-axis mean failure rate. As you can see, the aluminum capacitor is the most vulnerable component in an LED driver. And next vulnerable components is boost converter IC and diodes. In contrast, the resistor and inductor are the components with the lowest failure rate, even if the temperature is increasing. This is why aluminum capacitor contain electrolytes which sensitive to thermal stress. But resistor and inductor are less sensitive to thermal stress. We analyze the three types of all-node redundancy structure. The first one is type A. For type A, two LED driver modules per group, and it providing 100% redundancy. For type B, three LED driver modules per group and provide 200 redundancy, and type C, 4 LED driver module per group and provide 300 redundancy. The table on the right summarizes the feature of each type. As you can see, the higher redundancy has to handle the large maximum current of a single module. For example, type C has to handle a 960 milliampere when only one module left in the group. And the redundancy is calculated using equation 1. The denominator is the minimum number of modules required, and denominator is the number of spare modules available, and multiplied with 100%, and we can get a redundancy. Reliability analysis. First, we had to reflect the partial failure conditions. So we adapted using the Markov model. And we defined the failure as the case when all modules in a group fail. The left Markov chain is conventional method Markov chain. But in the conventional method, there are a total of 4,096 possible states. It's too many states to calculate the system reliability directly. So we use a group of Markov chain model as a single state. The figures below the Markov chain model for each type. Here, the number 1 means a normal condition for each module, and 0 means a failure condition for module. So the type A Markov chain configuration like this at type B and type C. As I mentioned earlier, the failure is all modules fail in a group. So here, the only last state is a failure in each type. This page shows changing in group failure rate according to number of module failure. The table on the left shows amount of current to module according to the number of module failure by type. For all types, the current is 240 milliampere with no failure. However, the current increases according to number of module failure. And the graph shows the group failure rate according to the number of module failure. Here, the blue line is type A, the orange one is type B, gray one is type C. As you can see, the type C slope of the failure rate increase is steeper as module failure. For example, the module failure from 1 to 2, the failure rate increases 0.02. However, from 2 to 3, the failure rate increases around 0.7. It's because the higher current will lead to a higher operation temperature. So higher redundancy level results a greater increase in failure rate like this. This graph shows the result of the reliability analysis for each type. Here, the black line is system reliability without redundancy, and red one is 100% redundancy. Blue one is 200% redundancy, and green one is 300 redundancy. As we know, it means all of the redundancy improves system reliability. Next, we evaluate the reliability based on the average lifespan at 67,000 hours for LED driver. The results show that the reliability difference between type A and type B is 0.33. And between type B and type C is increased 0.12. It means reliability does not increase linearly with redundancy. And it also means we have to consider thermal stress and components rating. Therefore, in this study, the type B combination is multi-suitable among proposed configuration, and the graph is blue line. Now, I'd like to draw a conclusion. We analyzed the reliability improvement of LED drivers according to redundancy combination in all of systems. And then all of the redundancy structure improve reliability. But it must consider the thermal stress caused by load shedding. And we could know increasing redundancy is not always efficient, and highlighting the need for a balancing among reliability, thermal stress, and cost from the components rating. Therefore, our future work will focus on proposing optimal redundancy configuration that take into account both price and reliability. This is my last page. Thank you for listening to my presentation.
Okay, thank you very much for your presentation. So, is there any question or comment from the audience for his presentations? So, maybe in your study, you consider the temperature as the main reason for the system failure. So I want to know, is there any other element that effect on the system failure excepting for the temperature?
Yes. Basically, we consider environmental conditions, right? So we can consider in a fight is 2022 guide like indoor condition and outdoor condition and dust and temperature. Yeah. So we assume that system contain indoor condition, and also so the dust and humidity basically considered but not detailed. So we focus on the temperature, like increasing by current. Yeah. As you know, the current is increasing junction temperature and components temperature. So, and the component temperature increase the failure rate of components. So we focus on the components temperature and dust and application install station consider a little, basically, yeah. We have the future work. I will consider about that in more detail.
Okay, thank you. So, is there other question or comment? Okay, if no other question or comment, so thank you very much for your presentation.